Hello, this is Mr. Henry, and welcome to lesson 5.4, using functions to model relationships. The essential question says, how do I use functions to model relationships? All right, so fairly straightforward as far as the essential question, although you may not know what it means. Functions to model relationships sounds kind of vague, which it sort of is. For our warm-up, we have a type 2. So I'll be grading on the correctness of your response. It says, using graphs, tables, or equations, give an example of one linear function, one nonlinear function, and one non-function. Okay? So I would be expecting 3 examples on your page. One that is linear, one that is not linear, and one that is not a function. And you may use graphs, tables, or equations to model that. All right? Go ahead, pause the video, do that. When you're ready, move on to the vocabulary, hit play, and we'll be moving on. Okay, so we have 2 vocab words here. First of them is a linear relationship, and this should look very familiar. So a linear relationship is a relationship that can be written in the form y equals mx plus b for all values of x and y. Now, that probably rings a bell. Y equals mx plus b. We called this something else in the past. We called that slope-intercept form. Slope-intercept form is the form y equals mx plus b, where m is the slope and b was the y-intercept of the line. Well, now that we're talking about it as a function, it's the same thing. We learned in the past couple lessons that functions can be represented as lines. They're linear, or can be linear, which means if it's a line, it has a slope, it has an intercept. Okay? So we'll be looking at these linear relationships. Initial value. This is something we've seen before, but probably not. I don't think it's been phrased like this in the past. The initial value is also known as the y-intercept. It's just the y-intercept of the line. It's the value of the function when x equals 0. So if we're talking about, a word problem, say, and somebody's painting a wall, and this is how the rate that he's painting. Well, at hour 0, he has this much of his wall painted. There's hour 1 and 2 and 3. Well, right here at hour 0, that is the initial value. That's how much he has painted before he's even started painting. Maybe he had some of the wall done from yesterday, or somebody else helped out or something. So that would be the initial value. That is the y-intercept. That's where this line is crossing the y-axis. Okay? So we will be looking quite a bit in this lesson trying to find initial values. The other thing that we're looking for, which I don't have it up here because it's a word we've already talked about, rate of change. We will be talking quite a bit about the rate of change of a function, because the rate of change is also known as the slope. So if we could find the rate of change, and we can find the initial value, which is the y-intercept, we can write the equation of that function in slope-intercept form. We can graph it. We can do all kinds of wonderful things to it. But it all starts with taking the scenario we're given, finding the y-intercept, which is the initial value, finding the slope, which is the rate of change, how fast it's changing, and then we go from there. Okay? So let's go ahead and get started. So example 1 here. It says, Jasmine is currently 200 miles away from home. She's trying to get home and is traveling at 60 miles per hour. Identify the initial value and the rate of change of the function. All right, let me do some underlining here. So we need to identify the initial value and the rate of change of the function. And then we're going to write an equation in slope-intercept form to represent the situation. Okay, that's not too bad. So we need to find the initial value and we need to find the rate of change. Okay, so the initial value is whatever the thing we're measuring, where is it when it starts? When the problem begins, what is the starting value, the initial value? Well, Jasmine is currently 200 miles away from home. So the initial value, her initial distance, is 200 miles. She's trying to get home and is traveling 60 miles per hour. That 60 miles per hour, that is a rate. That is a speed. That's how fast something is changing. The thing that's changing is her distance from home. So the rate is 60 miles per hour. All right. So we found the initial value. We've found the rate of change. The initial value is 200. The rate of change, so this, if we're talking about, this is miles. And this rate of change, her miles is changing by 60 miles per hour. Okay, the second thing it would like us to do is to write an equation in slope-intercept form to represent the situation. Okay, now this can be pretty easy. We're going to take these initial value and this rate of change. So, slope-intercept form, y equals mx plus b. M, your slope, is rate of change. Rate of change is a slope. So put it in there. B is your initial value. That's your y-intercept. That's where the graph starts. If we would graph this situation, I would have a graph that looks like this. She starts here at 200 miles away from home, and she's driving home at 60 miles an hour, and there we have like her, so this is her distance, this is her time. So she starts 200 miles away from home at the beginning of the problem, and after some amount of time, way down here, she gets home. Okay, so the initial value of the problem was 200. Now, this equation we have here is very close to right. The only thing that would make this different is that the fact that our slope needs to be negative. And going, why does our slope need to be negative? Well, if she's starting 200 miles away from home and she's trying to get home, this rate of change is how quickly she's getting home. So every hour, her distance is getting smaller. Her distance from home is getting smaller. So imagine, she starts off 200 miles away from home at 0 hours. Let me reverse this. 0 hours, she's 200 miles away from home. At 1 hour, well, how far away from home would she be? Well, she would be 60 miles closer than that 200. So 200 minus 60 gives you 140. And then in 2 hours, how far away from home would she be? Well, she'd be at 200 miles, and then she'd be 120 miles closer than that, which would put her at 80 miles away from home. And then at 3 hours, she would be 20 miles away from home. This is just an XY table representing this. I mean, if you think about it, if you plug in 0 right here for x, negative 60 times by 0 is 0, plus 200 is 200. Plug in a 1. Negative 60 times by 1 would be negative 60, plus 200 gives you 140. Okay? So this table helps represent that situation as well. That's why we need this negative, because her distance away from home is going down with each hour, not going up. So our change is a negative change. Our equation, our slope, our graph, our values are decreasing over time. So we need to have a negative rate of change. But that's it. I mean, we pretty much had it except for that negative sign with just the initial value being our y-intercept and our rate of change being our slope. Letter B. Last summer, Sean had a banister put on the front of his house. The carpenter charged a fee of $120 for the materials and $100 per hour to rip out the old banister and put in the new one. Identify the initial value and the rate of change, then graph the function. Okay, so a couple things here. So he was charged a fee of $120 for the materials and $100 per hour to rip out the old banister. So for identifying our initial value, and our, oh, I put too many T's in initial, I-N-I-T, let's just do that. Okay. Our initial value and our rate of change So let's think about it. The carpenter charged $120 for materials and $100 per hour. Well, that $100 per hour, anytime you're doing something repeatedly over and over and over and over and over again, that's going to be a multiplication. Okay, I can tell you right now, that will be our rate of change. That's our slope. That's how much the cost of this replacing the banister is going to change over time, because every hour this guy works on the banister, he's going to charge another $100, another $100. So over time, this is going to increase the cost. So that is our rate of change, $100 per hour. The initial value then would be $120, not just because it's the other number of the problem, but if we're getting this banister replaced, you have to buy the materials up front. So the carpenter is going to charge him $120 before the carpenter even starts touching the old banister, before he rips out the old banister and put the new one in. Okay, so the initial value is $120 because that's the starting value of the cost before any work is done. The rate of change is 100 because that's how much it's going to cost every hour with respect to time. Now it wants us to graph this. So we've identified the initial value and the rate of change. It says graph the function. Well, I don't know how to graph just this. But if we could turn this into an equation, like the last problem, then we'd have no troubles. So if we go, let's see, y equals mx plus b, y equals, all right, the initial value, the starting value, is our b. That initial value is our y-intercept. Our rate of change, how much it's changing every hour, that is our slope. And because this rate of change is increasing, every hour he's going to add more money. The cost is going to keep increasing every hour. We know this rate of change is going to be positive. All right. So now we have an equation. Now we graph. So when you're graphing, we've got what? Time and money. I think are the two things we're measuring. We're definitely measuring the total cost and the cost per hour. So time is always on the x-axis, the bottom, because it's independent. Oh, I can't do this on this tablet. Money, let's see. That's going to be very sloppy. There we go. Money. Okay, so time. Well, I mean, I don't exactly know what my unit of time is going to be. I assume it's going to be something just like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, let's try that. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And as far as my y-axis, my scale here, well, my initial value is 120. And I'm going to be going up by 100 every hour. I don't think it would make sense to go like 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Because that, if we count by tens, we don't even get the first initial value on there of 120 bucks. And because this is going up, increasing, I wouldn't get any other values either. Here's what I'm going to do. I'm going to count by hundreds. 100, 2, 3, 4, 5, 6, 7, 8, 9, and 1,000. So now my initial value at 120 would be roughly right about here, just above 100. So at time 0, cost 120 bucks before he even starts working. After 1 hour, he's going to go up by $100. So 1 hour, now it's going to cost me 220 bucks. 2 hours, 320 bucks. I'm using the slope of 100 over 1. So go up 100, up $100 over 1 hour. Up $100 over an hour. Up 100 over 1. Up 100 over 1. Up 100 over 1. Up 100 over 1. And I'm out of space. So the function would look something like, can I make linear? Close. That's roughly linear. So that would be my linear function because it makes a straight line. So the initial value, still the y-intercept. The rate of change is still the slope. Initial value is where the function starts on the y-axis when the x value is 0. The rate of change is the slope. It's how much change is happening, how much I go up for every time I go over. Like when I go up 5 and over 1, here I went up 100 over 1. That's that rate of change. And that was letter B. Letter C. A farmer is harvesting his corn from his field. Okay. The graph below shows the amount of corn still in the field while the farmer is harvesting his field. All right, let's look at the graph. All right, so corn left in the field in pounds and time. Okay. Write the function that is represented by the graph. Identify the rate of change and the initial value. All right, so we need to write the function. Then we need to identify rate of change and the initial value. Okay, so we need to write a function from this, write an equation from this. So, equation of a line, slope-intercept form. So y equals, all right, let's see here. So for slope-intercept form, you find your slope, you find your intercept. So see, my intercept appears to be at 4,000. So that's pretty easy. Slope. That's a point. That doesn't look like one. That could be right there. No, could be right there. That seems about right. That looks consistent. So my slope appears to be down. Now, don't do this. It's not down 2 over 5. You wouldn't say the slope is negative 2/5. That doesn't work. Using your scale, if you're going down 2, this is down 2,000 over 5 hours. So down 2,000 over 5, which we can simplify. If you take 2,000 divided by 5, we're going to get negative 400. If you don't believe me, we can check this. So 2,000 negative divided by 5 equals, that's a negative 400. So our slope is negative 400x. That's a 4. All right. So now we have the function represented as an equation. Write the function. Check. There is our function of how fast this farmer is harvesting his corn. So the slope is negative because the amount of corn left in the field is going down every hour. He's harvesting it, so there's less corn still in the field. Okay, it asks us to now identify the rate of change and the initial value. So initial value, rate of change. The initial value is where the graph starts on the y-axis, so that would be the y-intercept. So the initial value here, by looking at the graph, is 4,000. By looking at our equation, is 4,000. Initial value, 4,000. So it's that value, it's that value. The rate of change here is our slope. It's how fast he's harvesting, how fast the amount of corn on the field is changing every hour. And according to our graph and our equation, it's going down by 400 pounds an hour. And we can tell that based off our slope we did there and our slope we have right there. Sorry, I have arrows and lines going everywhere. But I mean, that's just showing, I was trying to represent how we found all that information. Might be too much. So initial value is our y-intercept, Our rate of change is this negative 400. That's this slope here. That's the slope of the graph here. That's how fast the amount of corn in the field is changing every hour. So what does the rate of change mean in this scenario? So in the last problem we did, we found the rate of change was negative 400. What does that mean? What does that represent? And I kind of just said it because I didn't know this question was coming up. But see if you can remember before you rewind the video and look at it again. What does the rate of change mean in that scenario? That scenario with the farm, we said the rate of change was negative 400. What's that represent? Go ahead, pause the video, answer that question. When you're ready to continue, hit play. We'll go through it together. Okay, so did you say that's the speed the farmer's harvesting his corn? Because that's what it is. That's how fast the amount of corn in the field is changing every hour. And it's only changing because the guy's harvesting. So if the guy would harvest faster, then his slope would be more like this. So he'd be done in like 4.5 hours instead of 10 hours. He'd be going faster. If he's harvesting his corn slower, he'd have a slope like this. And it would take longer to harvest the same amount of corn. So the slope represents how fast this guy was harvesting his corn. All right, letter D. So it says, Derek wants to work on an assembly line putting together electronics for an engine. He gets paid a daily wage plus an additional amount for every engine he puts together. The table below shows his daily earnings, Y, if he puts X engines together. Okay, so that's pretty cool because that actually tells us right now what the X and Y variables are. Y is how much money he earns every day. X is the number of engines he puts together. All right. So daily earnings Y, number of engines put together X. Write a linear function that models this situation. Identify the initial value and the rate of change, then graph the function. So there are 4 things it wants us to do in this problem. It wants us to write a linear function. It wants us to identify the initial value and the rate of change, then graph the function. There's 4 things we have to do here. So it's going to take us a little while. Okay, so to write a linear function, back when we talked about this previously, we learned we had to have slope and hopefully a y-intercept or a point or something else we can use. Well, just from the information we have here in this table, we don't have a slope, we don't have initial value, we don't have the y-intercept, but we can find those things pretty easily. So let's start with slope. To do slope, we need to use the equation for slope. M equals y2 minus y1 over x2 minus x1. This is our x values, this is our y values. So I'm just going to use these first 2 points. So this would be x1, y1, x2, y2. So 152 minus 141 over 2 minus 1. All right, so 152 minus 141 is 11. 2 minus 1 is 1, which means Derek's rate of change, his slope, the amount that his money changes every hour, is 11. He's getting paid $11 an hour. Maybe. Is 11 bucks an hour? Well, I don't know. It's 11 something. We'll figure out what this rate of change represents in this scenario. That's definitely the slope. And then, in order to continue writing this function, because we have our rate of change, we need the initial value. We need the y-intercept. Well, looking at this table, I don't see a y-intercept here. We don't have a graph to look at to find the y-intercept. So there's two ways we could do this. One way we could do this would be if we use point-slope form. So way back in module 4.9, lesson 4.9, there's a lesson that was all about writing the equation of a line in any form. Slope-intercept form, point-slope form, standard form. And the way the lesson worked out is if you had slope and a point, so any of these, there's 5 points here. Any of these 5 points, if you plug that in with your slope, you could change it into slope-intercept form. So let's do that. So we've got y minus y1 equals m times x minus x1. That is the formula for point-slope form. Slope is 11. And let's just use, we already have this labeled as x1, y1. So y1 is 141, x1 is 1. If we now solve for y, so we distribute 11x minus 11, y minus 141. We're going to add 141 to both sides. Y equals, let's see, 11x 141 minus 11 is going to give us 130. This is now the equation of a line. That is a linear function. And from this, well, write the linear function, check. Identify the initial value, check. My initial value here is 130. So that y-intercept is the initial value. There I go with arrows again. My rate of change is 11. We saw that up here. And then when we plug that same slope in, it stays the same even down here. That slope, that rate of change is there. Sure, I'll draw the arrow. Feels good. All right, so we've got the initial value of 130. We've got a rate of change of 11. And then we want to graph the function. All right, so let's see here. Graph this thing. Well, what would be their two units? Our x is the number of engines he put together, and the y would be his amount of money in dollars. So money. There we go. So let's see here. Well, our x only goes from 1 to 5. So 0, 1, 2, 3, 4, 5, and x went for good luck. And our daily earnings, well, it like starts at 141 and goes to 185. So, I mean, obviously counting by like tens won't work, because if we do like 0, 10, 20, 30, 40, we're only getting to 100. Okay, 50s, 0, 50, 100, 150, 200. No, because our biggest point is 185. We don't want 200 to be like that tall. So 50 was too much, 10 was too little. Nice number in between would be 25, 0, 25, 50, 75, 100, 125, 150, 175, 200. Sure, that seems about right. Let's do 25s. 25, 50, 75, 100, 125, 150, 175, 7, 200, 225, and 250. Now, even if we didn't do all this other stuff down below, let's ignore it for a second. I could still graph these 5 points. So 1, 141. We'll call it about there. 2, 252. Roughly there. 3, 363. Sure. 4, 174. 174 would be like right below there. 5, 185. So those 5 points are roughly linear. They're not linear because I'm not a machine at graphing. I'm close. See, they're pretty close to linear. Now, even from that, you could probably almost estimate the initial value. You could kind of work backwards and go, okay, something along that line. So it's be a little bit bigger than 125. We found the initial value was 130. That would be this point right here. That would be at 130. Okay. I want to show you a slightly different way of finding this initial value. So what we did when we did this problem a second ago is we used this point slope form. We plugged in a point and the slope. We solved for the y-intercept, or we solved for a slope-intercept form, and then the y-intercept was our initial value. Let's look at this logically. So I'm going to take this red stuff and move it. Group. Move over here, just out of the way for now. So let's look at this logically. So we've got a table here. The value of x is increasing by 1. The value of y is increasing by 11. That was the slope we found. Well, if every time this is going up by 1, up by 1, up by 1, and this is going up by 11, so this is plus 11, and then plus 11, and then plus 11. The initial value would be when this guy is 0. When we have an x value of 0, this would be our initial value, because when the x value is 0, that's the y-intercept. So if we do the reverse and we subtract 1 here, and what's the reverse here? Well, go backwards in the pattern. Instead of adding 11, if you subtract 11, 141 minus 11 is 130. So that's just a slightly different method. Instead of this stuff that we did, it's a slightly different way of thinking about it, using the pattern that they give us to find when the x value is 0, to find this initial value of the problem. All right, I'm pretty sure the next page has a couple questions about the same problem, so I'm not going to discuss too much because I think they're for you. So, first one says, what does the initial value represent in the scenario, and what does the rate of change represent in this scenario? So back here, what does this initial value, 130 bucks, represent, and what does the rate of change, this 11 something, represent in this scenario? Go ahead, pause the video, try to answer this on your own. You're trying to interpret the scenario now that you have all the information given to you. What is the initial value, and what is the rate of change? What does it mean? Not just the initial value is 130 and the rate of change is 11. No. What does it mean in terms of the scenario? What does it represent for this Derek guy who's putting these engines together? How does it affect his life? What do that 130 and that 11 have to do with Derek? So just go ahead, pause the video, try this on your own, really think about it, look back at your own notes, and figure out what those initial values and that rate of change represents. When you're ready to continue, hit play, and we'll go through it together. All right. So hopefully you found the initial value here would be, since we're talking about the number of engines he put together and the money, this initial value would be how much money he makes after he's put no engines together. He's done no work. He gets paid 130 bucks. So that would be he gets paid a daily wage plus an additional amount for each engine. That 130 bucks is his daily wage. That 130 bucks is how much he gets paid whether he puts any engines together or not. He shows up to work that day, he's conscious, he gets paid 130 bucks. Okay? Now he also gets an additional amount for every engine he puts together. How much? Well, let's see. If he puts together one engine, he's getting $11 more. If he puts two engines, he gets $22 more. He puts three engines together, he gets $33 more than just the daily wage. So every engine he puts together, he's making an additional $11. So this 11 is how much money he gets for each engine he puts together. So the initial value was his daily wage. Was it CKS? Derek, yeah. Derek's daily wage. And then the rate of change is the amount of money Derek gets for each engine he puts together. For each engine he puts together. And so he gets $11 per engine, and he gets paid $130 every day. So $130 a day and $11 an engine. That's what that initial value and that rate of change mean. Letter E. When the police find a dead body, they will often use the temperature of a person's liver to find their time of death. The graph below shows a person's liver temperature after their death with respect to time. Identify the initial value and rate of change. Then write the equation in slope-intercept form. Okay, so verbs. Identify the initial value and the rate of change. Write the equation in slope-intercept form. There are three things they want you to do. This problem is for you to do. I would like you to do it now. I'll show it again. Please find the dead body. They will often use the temperature of the person's liver to find their time of death. The graph below shows a person's liver temperature after their death with respect to time. Identify the initial value and the rate of change. Then write the equation in slope-intercept form. Go ahead, pause the video, do those three things right now. When you're ready to continue, hit play, and we'll go through them together. Okay, so let's see here. So we're going to need to find our initial value, and we need to find our rate of change. So let's see, initial value is the y-intercept. So that is here. It's not 40, it's not 35, maybe call it 37 degrees Celsius. And rate of change. So how much is this changing? Well, let's see. Well, that's a nice point right there. I'm trying to see if there's any other nice points that I know exactly what they are. That could be, but let's just use this one and this one. So if we're calling that first one, sorry about that. If we're calling this first one 37, so we'd have 2 points. 37, 0, 37. So when the time is 0, the temperature is 37. And when the time is 5, the temperature is 30. And from those 2 points, we could find slope using our slope formula, which is m equals y2 minus y1 over x2 minus x1. So we've got x1, y1, x2, y2. This is the x and y value of the first point, x and y value of the second point. So y2 minus y1 over x2 minus x1, giving us negative 7 over 5, which usually rate of change, slope you leave as a fraction, but let's just quickly see here. Clear. 7 negative divided by 5 equals negative 1.4. Or negative 1.4, just because I think the decimal will make more sense here in a second. All right, so we have our initial value, we have our rate of change. Check, check. Write the equation slope-intercept form. All right, we can do that. We have everything we need to do that. Let's group that stuff and move it out of the way a little bit. Move it down here. All right, so let's write this. So slope-intercept form is y equals mx plus b, y equals slope. That's the negative 7/5 x plus b, which is 37. So that would be our equation represented by this graph. Okay. Again, I'm not going to discuss too much. I really want to. I'm not going to discuss too much because it looks like the next page or so has some questions about this problem, like what does the initial temperature represent and what does the range of change represent, and that kind of stuff. So let's do that. First one, what does the initial value mean in this situation? So the initial value we said was 37 degrees Celsius. What does that initial value mean? Well, think about it. This is a person who has died. This is the number of hours since they've died. So this is 0 hours when they died, after they've been dead for 1 hour, 2 hours, 3, 4, 5, blah, blah, blah. So the initial value right here is when they've been dead for 0 hours. Right now, you're listening to this, you're dead for 0 hours. You are not dead at all. So the initial value would be the temperature of their body when they're not dead. That's the temperature when you're alive. Your body is roughly 37 degrees Celsius right now. Okay? And here I have a little thing from Google. I just typed in, actually, it's not what I searched for. I searched for 37 degrees Celsius, and it pops up at 98.6 degrees Fahrenheit. So, that's the average body temperature of a person is 98.6 degrees. All right? So initial value is the temperature of the person when they're alive. Initial value. Let's do body temp. Body temp when the person is still alive. And since the question doesn't ask, but I want to talk about it anyways, what does the rate of change represent? This negative 7/5 or this negative 1.4, depending if you like the fraction or the decimal. What does that mean in the scenario? Well, now we're talking about the time of death. So every hour, there's a change of this much. So every hour after this start of 37 degrees, it's going down by 1.4. The next hour, it's down another 1.4, down another 1.4, down another 1.4. So that rate of change would be how much the body, the liver temperature, cools down with respect to time. So that's how they can decide, like, oh, this person's been dead for 8 hours. If they stick the temperature, like a big meat thermometer, in the person's liver, and at 8 hours, which is roughly here, if they look at it and go, oh, this guy has a liver temperature of 25 degrees, I'm estimating, it's about there, they say, well, this person's been dead for about 8 hours. And that's how they can figure these things out. Okay? For our summary here today, we have a type 1 with 2 minutes on the clock, and it says, in what ways did we use functions to model relationships throughout this lesson? There you go. Just basically it's a summarizing of the lesson. So how did we use functions to model relationships throughout the lesson? Go ahead, pause the video if you need the question a little bit longer. If not, this has been lesson 5.4. Thanks for watching.